Hello everyone. Hi, how are you? I hope everyone is doing good. So welcome to another video of plant water relation. Uh, in the previous video, we were talking about the various mechanism of water absorption by the plant, that is the root system. Now, like example, diffusion we discussed, okay, and then we also discussed about the osmosis. Now, in continuation to that, we will be discussing about the type of osmosis. We have covered the hypotonic solution, isotonic solution, with respect to osmosis. Now we will discuss about endo and exoosmosis in this video. With relation to that, we will be doing osmotic pressure, facilitated diffusion, water potential, and plasmolysis. Basically, these are short, concepts. We will just be doing the definition and understanding it with an example. Okay, so these are short topics, very short topics that we need to know for a further understanding of the uh, topics which will be coming under this chapter. Okay, so let's begin with the first category, that is we will now discuss about endoosmosis and exoosmosis. Before that, what is osmosis? Movement of, yes, take a take 5 seconds and just recollect, so that I will also mention. So what is osmosis? Basically, osmosis is movement of solute. It is movement or solute or the solvent, okay, from lower concentration, from lower concentration to high concentration. Okay, this is exactly opposite to diffusion. In diffusion, what we saw movement of ions, molecules, solute molecule, okay, atoms from higher concentration to lower concentration. Okay, whereas what happens in osmosis, mostly the solvent, the water, will move from lower concentration to higher concentration. Okay, yes. So wherever there is higher concentration of solute and low concentration of solute over here, the tendency of movement of water will be in this direction. Okay, here the solute concentration is less, here the solute concentration is high. So basically, it is the movement of solvent and water. Okay, now in that we have two types, that is endoosmosis and exoosmosis. Now the name itself will suggest its meaning. Endo means inside, movement inside. Okay, inside the cell, you can say. Here the example that we have taken is in a container there is water and there are raisins. Raisins are kishmish. Okay, these are a type of dry fruits. Basically, grapes are dried. Yeah. So when you soak kishmish, when you soak raisins in water, you might have observed also what happens after some time. Let's say keep it for 3 hours or 4 hours or overnight, let's say. So what happens to that raisins which are shrink, which are dried, sun dried, after certain time they will swell up. The raisins are swollen. So what has happened? Common understanding, anyone will say the water from the container has moved, some amount has moved inside the raisin cell, okay, until it becomes fully swelled up. So endo is basically the inflow inside, water, movement of water from the outside to the inside. Okay, here you can, water and solvent will be interchangeably used, because here the outside environment that we are taking is solvent. Basically we are taking plain water only. So into the cell from the outside, okay, when a cell is placed in a distilled water, so what will happen? Cell will swell up in this case. Yeah. Then what happens in the next case? You take now grapes. Okay, you take grapes which are in fresh state, and you now put it in a solution. In a solution, I'm telling, not pure water. In a salt solution, you can take sugar solution also. That's not a big deal. So let's say you have taken a salt solution. a solution in which you have dissolved salt, and you have taken what? Grapes. So normal fresh grapes, okay, not these sun-dried ones. Now what will happen to this? Okay, here we can take only salt solution because already sugars are present in the grapes, so we will take only salt solution. Now you take a salt solution, you dip the grapes. After certain period of time, what you will see, the raisin will shrink. The raisin will what will happen to the raisin? The raisin will shrink. Okay, what has happened? Outflow of water from the grapes has taken place. That is from the cell, you will say. Okay, we will just say cell. When placed in a more concentrated solution like sugar solution or like your salt solution, okay, the solution has to be hypertonic. Okay. Now, when you take a normal fresh grape, what happens in the normal fresh grapes? Inside, the water content is more, right? The water content is more. When you dip this fresh grapes into a solution which is having high solute concentration, either salt or sugar, what will happen? Here, the water is less. The amount of water in the solution is less. Here, the grapes had amount of water more. So the movement of water will be from the grapes into outside the in the outside direction in this solution. Okay, so outflow of water will take place from the cell which is placed in a hypertonic solution. I hope you know what is hypertonic solution, wherein the solute concentration is more than the solvent concentration. Solvent is less. In hypertonic, solute concentration is less, solvent concentration is more, and in isotonic, both the solute and the solvent are balanced out. तो क्या होगा इस केस में? The cell will shrink because the water has gone out. The water has gone out, so the cell will become shrink. In the endoosmosis case, the water has moved in, so the cell will swell up. Okay, so that's the two major types of osmosis. Okay, based upon where in which solution, whether you put it into the pure water or a hypertonic solution, you will see the swelling up or the shrinkage of the grapes or the cell. Okay, similar phenomena happens in absorption also when the root system is absorbing water. Fine. So there are certain terminologies that we will see further. So we will just define endoosmosis once again. Entry of water molecules into a plant cell, okay, kept in a solution having lower solute concentration than that of the cell sap. Here with respect to plant water relation, we are defining it. So entry of water molecules into the plant cell, okay, when the solute in the plant cell is low, okay, we call it as the cell sap. Yes, basically inside the root system there is a hypotonic solution. So what will happen? Water from the environment will move inside the root system. Water from the environment will move inside the root system. Okay, when the solute inside the root system, the cells of the root system, the cell sap is solute is low, so automatically water will move inside, causing swelling. Another word is becoming turgid. Swelling is becoming turgid. Another word for swelling is becoming turgid. What will happen when this the cell swells? Okay, so you have the cell, let's say this is the plasma membrane and this is the cell wall. Okay, when the cell is swelling, there is a pressure created on the cell membrane, there is a pressure created on the cell wall. Yes or no? When something swells, okay, for example, you put on extra weight over a period of time, you feel all your body parts have become so heavy. Okay, you feel so difficult to move around, to do any exercise, your stamina goes down. Okay, so there's a pressure created from your, it's a very layman type example, but still, okay, so there is a pressure created. For example, you take a balloon, you fill water inside a balloon, okay, and what you will see, there will be a certain point you will feel that after this I should not be adding water. So So there will be a pressure created on the cell membrane and the cell wall. Yes, so that is known as turbo pressure. Basically, on swelling, on become turgid, that pressure which is created will be TP, that is turgor pressure. Okay, in a fully turgid cell, DPD is 0. Remember what is DPD? In the previous videos when we were doing diffusion and all that stuff, we also discussed this term, diffusion pressure deficit. What is this? In simple terms, I will just recap it. Uh, it is basically the thirst of the cell. Remember that last line that we quoted? DPD is basically the thirst of the cell, how much water it can draw from the environment. So when it is full, when it is satisfied, satiated with water, basically there is no further space to bring in more water, so that's the diffusion pressure deficit. So when a cell becomes fully turgid, it has swollen to its extent, now no more water can come inside, otherwise the cell will burst. I mean, just in a common understanding. So at that time, what is DPD? 0, because now this thirst has been quenched in that manner. Okay, so in a fully turgid cell, the DPD will be 0. Fine. Cell wall is thick, rigid, and exerts a counter pressure on the cell sap. This is called wall pressure. So inside environment, inside cytoplasm is filled with water, that is creating pressure, and the cell wall is like reached to its maximum boundary. I mean, it is swollen up, and that's also like full. Now it cannot expand more. So that also creates a pressure which we call it as wall pressure, WP. Okay, wall pressure, but it will be in opposite direction. Okay, so in a fully turgid cell, the turgor pressure and wall pressure will be equal, but they will have an opposite direction. The wall pressure is directing its pressure towards inside, and the inner cytoplasmic cell membrane, the sap pressure, is directing its pressure towards on the cell wall, and the cell wall is directing its pressure on the interior of the cell. So they will be equal, but will be in opposite direction. Okay, this happens in endoosmosis. What happens in exoosmosis? Exoosmosis में water moved out, right? So the loss of water molecules from a plant cell placed in a solution having high solute concentration. The example we took was of the salt solution. Then that of the cell sap, that is inside the solute is less, outside the solute is more. Means what? Inside the water is more and outside water molecules are less. So the water will move from inside of the cell to the outside. Okay, in a hypertonic solution, then this will be known as exoosmosis. In this case, the cell becomes shrink, or not shrink, we can say flaccid also, like chapat. The water is less, so the flattens kind of. The cell becomes flattened. So flaccid. So these are the two terms. Moving forward, which brings us to this creates an osmotic pressure. Okay, so because of these osmosis, either endoosmosis or exoosmosis, there is a pressure created which will be known as osmotic pressure. So what is this? It's a pressure of the solution which is required in opposite direction. Okay, a pressure of the solution which is required in opposite direction to stop the entry of the solvent molecules in the cell. As you can see in the illustration and in the figure on the screen, let's say if this is the semi-permeable membrane of the cell. Okay, yes, so this is the water is moving inside. As you can see, the solute is concentrated over here, solute molecules. The water will move inside, right? Because outside the solute concentration is almost negligible. So water is moving inside. Now you can see the solute rises. So a pressure will be created. Yes, a pressure will be created to stop the entry of the solvent molecules into the cell. So there will be a time wherein there will be no movement of water inside the cell. So at that time, we will say the osmotic pressure is in action. Okay. So what will happen over here if we bring back the diffusion pressure deficit? This will be equal to osmotic pressure minus the turgor pressure. Okay, that is the thirst of the cell. How much more water molecule does it requires? So that will be osmotic pressure minus the turgor pressure. So whatever is the value that comes, that amount of that will be equal to the amount of water molecule required. Okay, that is diffusion pressure deficit. Okay. In this, we can equate with the following equation. These are the representation or statement that you need to just know, okay, as and when we are going through the concept. So this we had earlier equated that the wall pressure and the turgor pressure is equal only in the previous slide. So if DPD is osmotic pressure minus turgor pressure, you can replace TP with wall P. Wall P, WP. Okay, that is the turgor pressure and wall pressure will is equal. So in place of TP, you can write WP also. You now the new equation you get is DPT is equals to OP minus WP. Okay, so what happens in a flaccid cell wherein the water has moved out, the turgor pressure is zero. There is no turgor pressure, there is no wall pressure, right? So this is zero. So DPD will become equal to only OP. This is zero, right? The TP is zero in case of flaccid cell, okay, whose water molecule has moved out and the cell has become flattened. So you are left only with DPD, that is the diffusion pressure deficit, will be equivalent to the osmotic pressure which is there on the cell. And whereas in the turgid cell, the DPD is zero, right? Because the cell has completely swollen, completely turgid. So their turgor pressure and osmotic pressure will be the same. Yes or no? Their turgor pressure and osmotic pressure will be the same. It will only change in case of a flaccid cell. Fine. So these are certain equations or certain statements that you need to know with respect to the endoosmosis, exoosmosis, what happens in endo, what happens in exo, and the osmotic pressure changes with respect to endo and exoosmosis. That is in a flaccid cell and in a turgid cell. Okay. Now we move to the next terminology, that is facilitated diffusion. Diffusion, we know, movement of ions, atoms or molecules from a region of higher concentration to lower concentration. No energy is required, no carrier is required. But when you talk about facilitated diffusion, when you add this term facilitated, so इसमें क्या होता है? Facilitated means someone is facilitating it, someone is helping out, someone is acting as the middleman or someone is acting as a carrier. So here what will happen, a carrier is involved. Okay, the absorption of solute, passive absorption, no active absorption, passive absorption only. When mediated by a carrier, then it will be called facilitated diffusion. Simple diffusion is like movement from higher concentration to lower concentration. So the movement will take place simply. No one is involved over here. Automatically a concentration gradient has been set up, so movement will take place in this direction. But facilitated, there will be carrier molecules. As you can see over here, in diffusion, this is happening. In facilitated diffusion, a carrier molecule, mostly protein molecules embedded in the lipid bilayer, will do this work. Okay, so here also you can see simple diffusion, movement of particles from higher to lower, outside of the cell to inside. And here proteins are there, channel proteins are there, carrier proteins are there. These are facilitated diffusion. So they will go through a gate or a protein. Okay. Particles that are lipid soluble can easily diffuse through the lipoproteinous shell membrane. Okay. We have discussed this in detail elaboratively in lower standards in the 11th standard when we were discussing lipid bilayer. Go and revise that topic first if you have certain doubts. Okay, you will understand this in a more better manner. So the diffusion of hydrophilic solute has to be facilitated because their diffusion across the membrane is difficult. Okay, what do we mean by this point and this point? When this is easy when these molecules are lipoprotein in nature. when they are lipoproteinic in nature. They can easily cross the lipid bilayer because this is made up of lipid and protein. Yes, but what if these molecules are, let's say, hydrophilic, water loving, and these are hydrophobic membranes, right? So they will be facilitated by either these carrier proteins. Okay, so they will be moved inside and outside through carriers. Fine. If the molecules are hydrophilic, water loving, so it becomes difficult to just simply, because oil and water, they are immiscible thing. Yeah, that is, they cannot gel together easily. So it becomes difficult. So it has to be facilitated through a carrier protein. So this is what we understand by facilitated diffusion. Then next we move to water, something known as water potential. This we have discussed in the previous video. Certain points extra that we will be adding over here is that basically water potential, recapping it, what it is, every component of a system, whether we are talking about any system or osmotic system or a diffusion setup, okay, there will be some amount of free energy which is used to do work. Now, this you will be discussing, you will be going into more detail in your chemistry class. So we will be discussing only those points which are relevant with respect to biology, okay, which we might be using it in further videos. So only those pointers we will discuss here. Rest you will be discussing it in detail in the chemistry class. So water potential, some amount of energy is there in every system to do work. Okay, that is known as a chemical energy, or here with respect to living science, we also call it as water potential. Okay, basically it is because of the osmotic movement of the water. This is because this is based on free energy. No energy is required. Water can move from from hypertonic, from a hypotonic solution to a hypertonic solution without any investment of energy. So that free energy per molecule is its chemical potential. Is its chemical potential, which is also called as water potential. Okay. So when you talk about a plant cell, the water potential in the protoplasm will be equal to the diffusion pressure deficit. Will be equal to what? The diffusion pressure deficit. That is how much amount of water is required to, swell up the cell. So that will be equal to the water potential of the protoplasm, but opposite in sign. That is, this water potential will have a negative value to it. Okay, because the water will always flow from less negative to more negative. Means what? If let's say -1 we write over here and -4, so which is less negative? If I tell you which is the bigger number over here, so you will write this, because on the number scale -1 is more. So this is what? Less. So from less negative to more negative. So the movement of water will be in this direction. Okay, so like that. Fine. That is from high water potential to low water potential area. Wherever there is high chemical energy, or this water potential, we are talking in this in with respect to osmotic movement of water. Okay, osmotic movement of water. So from high to low, it will be moving. Fine. So this is how the movement of water with respect to osmosis will take place in any system. So like this, you can see. Simple to understand. I think this picture will give you a fair idea. So the net movement of water will move to and fro, but the actual, when you calculate how many molecules of water have been moved from one side to the another, here the water molecules are more, if you will see. Yeah, these are the water molecules. So they are more over here. Solute is less. You just see 1 and 2. Here the solute is more. Yes, and water molecule is less. So here water molecules are less. Water less means low water potential. Simple. Water is more on this side. Water is more high on this side means what? High water potential. What is the tendency of the movement of water? From high to low. That is what I was trying to explain in the previous slide. from high to low. Net movement of water will take place from high to low. Okay, in this direction. So the equilibrium will be attained when water molecules from this side to this side moves. Okay, I hope that's understandable. And lastly, we move to the last terminology, that is plasmolysis. Very nice and short and simple topic. Lysis stands for breaking. Plasmo stands for the plasma membrane, you can say, okay, or the protoplast basically. What happens in plasmolysis? Basically, it is in connection to exoosmosis. When exoosmosis in a living cell happens, okay, and we know when does exoosmosis happen? When you place the cell in a hypertonic solution, not in a hypotonic solution, but in a hypertonic solution, then plasmolysis will happen. So that flattening of the cell, now, when we are talking about that flattening of the cell, so that is one step to plasmolysis. When you keep it for a more period of time, then the cell shrinks beyond repair. The cell shrinks beyond repair. Then plasmolysis happens. So it's a second degree version of flaccidness. So first there will be flaccid cell, which will lead to plasmolysis. So during plasmolysis, protoplast of the cell shrinks and recedes from the cell wall. So it just leaves the cell wall and just comes in one corner, okay, which results into flattening of the, like it's interchangeable, flattening and plasmolysis. Okay, fine. So as you can see in the diagram, what is happening over here, in this diagram, you have the normal cell. This is the cell wall, and this is the protoplasm, and cytoplasm is inside. Okay, slowly and steadily you see contraction of the cytoplasm. Can you see? It is leaving the cell wall here. It is leaving the cell wall here, and finally, in D, what has happened? Everything has come to one place. All this is, plasmolized solution. When will this happen? When you place this cell in a hypertonic solution. So what is happening? Water from here is moving out. Water from here is moving out. Because outside in the solution, water is less. Because outside in the solution, water is less. This is happening. This case is happening. Okay, when you place it in a hypertonic solution, plasmolysis will take place. Water moving out. Water moving out. Okay, shrinking of the protoplasm. This key word you should be knowing. Shrinking of the protoplasm is the plasmolysis. And in a plasmolysed cell, the turgor pressure is always zero. There will be no pressure as such which will be there. So turgor pressure will be zero. And when you put this cell, which has plasmolysed in a hypotonic solution, in this solution, more water outside, less solute in that solution, endoosmosis will occur and make the cell turgid. Okay, so it can be reversed. Okay, if the cell has not been damaged completely. I just mentioned when the flaccidness leads to plasmolysis, and then it is beyond repair. Okay, the damage is done. But if the damage is not too much, I mean there is no breaking of any organelles or any part, it can be reversed. You can take the cell, this plasmolysed cell, and put it into a hypotonic solution where more water is there outside. So what will happen? The water will move inside and rejuvenate the cell. This is known as deplasmolysis, and it will result into a swelling of the cell. Okay, swelling of the cell. And in a fully turgid cell, we know that the turgor pressure is equal to osmotic pressure, and hence the diffusion pressure deficit is always zero. So that's all with respect to plasmolysis. In the next video, we will be talking about the pathways of water, how the water moves inside, what route what path does it takes to reach the interior of the cell. So there are two pathways, apoplas and symplas, very simple. We will also cover what is active absorption and passive absorption with respect to the movement of water in the root system. That's all for this video. Thank you. Take care. Bye bye. See you in the next video.